Scientists studying the largest glacier on Earth have started using two words they almost never use, any day now. The floating shelf of ice that has been holding back Antarctica's Doomsday Glacier is fracturing, pulling away, and could break apart this year. It is pinned to the seafloor by a single point, and 20 years of spreading cracks have nearly torn it loose. When it finally goes, it will not raise the sea overnight. It will do something far worse. In the next few minutes, I will show you exactly what that is. A slab of floating ice at the edge of Antarctica is about to break apart, and the scientists who study it are no longer talking in terms of decades. They are saying it could happen this year. Some of them are saying it could happen any day now. That slab is the Thwaites Eastern Ice Shelf, and for as long as it has held, it has been acting as the one thing standing in front of the largest and most dangerous glacier on the planet. The people who watch it most closely have started describing it the way you would describe a dam with a widening crack running through the wall. The question is no longer whether it fails. The question is when and what happens the moment it does. Thwaites Glacier sits in West Antarctica, and it has earned a nickname that tells you everything about why researchers lose sleep over it. They call it the Doomsday Glacier. It is the widest glacier on Earth, its front stretching about 120 kilometers across, roughly the size of Florida or Great Britain, and it is close to 2 kilometers thick. That is a wall of ice more than a mile from top to bottom, spread across an area the size of an American state. And right now, the floating shelf that has been holding part of it back is fracturing and pulling away from the main glacier. This is not a forecast about the end of the century. Multiple scientists are pointing at the calendar we are living in right now, and they are doing it with more certainty than they had even a year ago. The thing you have to understand about this shelf is how little is holding it in place. The Thwaites Eastern Ice Shelf floats out in front of the grounded glacier, a slab about 350 meters thick extending over the open ocean. It works like a cork wedged into a bottle, or a buttress leaning against a wall. It presses back against the moving glacier behind it and slows the rate at which all that grounded ice can slide into the sea. Take the cork out, and what was being held back is suddenly free to move. That is the entire function of this shelf, and it is the entire reason its failure matters. Here is the part that sounds almost impossible. That entire floating shelf is pinned in place, in large part, by a single point. There's one spot where the seafloor rises up into a submarine ridge, and the underside of the ice catches against it, like a fingernail hooked on a ledge. One contact point on the bottom of the ocean is doing much of the work of restraining a shelf that is bracing a glacier the size of Florida. And a floating slab only 350 meters thick is holding back a body of ice more than 5 times its own thickness. When you lay it out like that, the alarming thing is not that the shelf might fail. The alarming thing is that so much has been resting on so little for so long. A single anchor, one ridge on the seabed, has been carrying a load the size of a country. Anchors like that do not fail gradually forever. At some point, they let go all at once. The reason scientists can now say the breakup is close comes from a study published in 2025, and it did not guess. It measured. Researchers pulled together roughly 20 years of data from 2002 to 2022, combining satellite observations, ice flow speed measurements, and GPS instruments planted directly on the ice. They watched what the fractures inside the shelf's shear zone did over 2 decades, and they tracked them the way you would track a crack creeping across a windshield, frame by frame, season by season. This is not a snapshot. It is a time-lapse of a structure coming apart. The shear zone is worth pausing on, because it is the weakest seam in the whole structure. It is the band where the floating shelf grinds against slower ice and rock at its edge, and that grinding concentrates stress into exactly the place you least want it. A crack in the middle of a solid sheet can sometimes stall. A crack running through the seam that holds the sheet to its anchor is a different kind of problem, because it works directly against the one connection keeping everything in place. What they found is that those fractures have been growing steadily, year after year, and that their growth has been quietly weakening the shelf's grip on its single pinning point. Every season of spreading cracks loosened the hold a little more. The surface and underside of the shelf are now described as heavily fractured, laced with cracks, and visibly detaching from the glacier behind it. The study's conclusion is blunt. The shelf is likely to break apart within about the next 5 years, and other researchers put the window even sooner, as early as 2026. Robert Larder, a marine geophysicist at the British Antarctic Survey, has said plainly that the shelf is very likely to break up in 2026. This is not a fringe prediction from the edge of the field. This is the considered read from people whose entire job is watching this exact patch of ice, and their confidence has been going up, not down. Now, if you have been paying attention, you might be waiting for the obvious objection, so let me get ahead of it. The shelf is already floating. And a floating object, when it melts or breaks, does not raise sea level because it is already displacing its own weight in water. Drop the ice cubes in your glass, wait for them to melt, the water does not overflow. So if the Thwaites eastern ice shelf shatters tomorrow, the ocean does not jump the next morning. That much is completely true, and any honest account of this story has to say it out loud, because getting that detail wrong is how people end up either panicking over the wrong thing or dismissing the whole warning as hype. But that is exactly the trap in this story, because the shelf was never the threat. The shelf was the break. What sits behind it is the threat. The glacier itself is grounded on land, resting in a basin that lies well below sea level, and it holds an amount of ice that is genuinely difficult to picture. As long as the shelf is there, pressing back, the glacier creeps forward slowly. Pull the break off a body of ice the size of a country, and it begins to accelerate toward the sea. That acceleration is the danger, not the shattering of the shelf. And here is the cruel part of the physics. Because oceans and ice sheets respond slowly, the rise that follows is described by scientists as largely committed, a consequence that keeps unfolding for centuries once it is set in motion, even if the world stopped warming tomorrow. So, the breakup itself is not the disaster. The breakup is the starting gun for something that does not stop when we want it to. To understand why the pinning point is failing at all, you have to look at what is happening underneath the ice, where no eye ever sees it. The ocean around West Antarctica is not uniform from top to bottom. There's a layer of relatively warm, salty water that sits far below the cold surface, and it is able to travel along the seafloor and reach places you would never expect ocean warmth to reach. Because the glacier and its shelf sit in basins carved below sea level, that warm water can push far inland underneath the ice, right up against the anchor points and grounding zones, and melt them from below. The attack does not come from the sky. It comes from beneath. This is why the single pinning point is coming loose. It is not being sawed off from above by warm air. It is being eaten away from underneath, at the exact spot where the ice grips the seafloor. And that warmth is not local or mysterious. The oceans have been absorbing roughly 90% of the excess heat trapped by greenhouse gases, and they cover more than 70% of the surface of the planet. That heat has to go somewhere, and some of it is going to the underside of Antarctica's most vulnerable glacier. We can even see this shift in the sea level record itself. A recent budget study found that ocean warming, through thermal expansion, accounts for about 43% of the total rise over the past 60 years. But that the balance has been changing, with melting land ice taking over as the fastest-growing driver since the 1990s. The ocean is both the weapon and the evidence, which raises a question that used to be nearly impossible to answer. How do we even know what the bottom of Antarctica looks like? For a long time, the terrain hidden beneath kilometers of ice was one of the least understood surfaces on Earth. That changed in 2025 with the release of a map called BedMap 3, and it is the most detailed picture of Antarctica's bedrock ever produced. The scale of the effort behind it is worth sitting with. It folds together every data set gathered since the 1950s, plus 84 new airborne surveys flown by 15 different data providers, adding about 52 million new measurement points and roughly 1.9 million line kilometers of radar. That is around 60 years of data, collected by planes, satellites, ships, and historically even sleds pulled by dogs, all assembled into a single map. It reveals about 27 million cubic kilometers of ice, thick enough in places to reach nearly 4.8 kilometers, and it narrowed the average distance between any point on the map and a real measurement down to about 5.6 kilometers. And that map revealed something that reframes the whole threat. There are, in a sense, two Antarcticas. Much of East Antarctica sits on bedrock that stands above sea level, solid ground beneath the ice, but large sectors of West Antarctica sit in basins that plunge far below sea level, and Thwaites sits in one of the worst of them. This is the geometry that lets the warm water in. And there's a second tool sharpening the picture, a climate dataset called PolarRes, built by combining 4 state-of-the-art regional climate models at roughly 11-kilometer resolution, tuned specifically for Antarctica's difficult coastal weather. It does not predict any one glacier's collapse, but it feeds better information into the ice models that do. Better measurements were supposed to calm the picture, the way sharper instruments usually shrink uncertainty. Instead, every improvement has revealed more basins below sea level and more pathways for instability than anyone had mapped before. The clearer the view has gotten, the more dangerous the setup has looked. Here is where the story stops being about one glacier and starts being about a continent. Thwaites is not just large, it is positioned as a keystone. It braces the glaciers around it, the ones draining the Amundsen Sea sector of West Antarctica. And if Thwaites retreats far enough, it stops holding them too. Remove the keystone from an arch, and the arch does not lose one stone. The whole arch comes down. In the same way, a full Thwaites retreat could unbuckle a much wider stretch of the West Antarctic ice sheet and let enormous volumes of inland ice flow toward the ocean. This is why a single glacier gets treated as a threat to every coastline on the planet. Its neighbors in the Amundsen Sea sector, glaciers like Pine Island, are already among the fastest changing ice on Earth, and Thwaites is the one standing at the gate. If the gatekeeper steps aside, the ice behind it does not have to wait its turn. It can all begin moving toward the same ocean at once, and there is no larger structure downstream to catch it. The mechanism that makes this self-sustaining has a name, and it is the reason scientists treat Thwaites as a runaway risk rather than a slow leak. It is called marine ice sheet instability. Because the bed under the glacier slopes downward as you go inland and lies below sea level, the grounding line, the boundary where ice lifts off the bed and starts to float, can retreat into ever lower water. Thicker ice at the grounding line discharges faster, which drags the line back further into still lower basins, which makes the ice there thicker and the discharge faster again. It feeds itself. Once it truly begins, there is no obvious break left to apply. The models that best capture how Thwaites has actually behaved show thinning already reaching about 100 kilometers inland along the glacier's long trough, which is exactly the fingerprint you would expect if this process has already started to turn over. In March of 2026, another study put numbers on where this leads, and its most unsettling finding is not a single figure. It is which models we should believe. Researchers led by Goldberg ran 2 independent ice sheet models, calibrated against how Thwaites actually changed between 2004 and 2017, and projected the glacier forward to the year 2067. They found that Thwaites could reach annual ice losses of roughly 180 to 200 billion tons per year by the 2060s. To be clear about what that means, that is close to the amount of ice being lost by the entire Antarctic ice sheet today, coming from this one glacier alone. One glacier on track to match a continent. But the truly uncomfortable part is this. The models that best match what Thwaites has actually done in the real world are also the models projecting the largest future losses. Normally, when scientists want to be careful, they hope the scariest scenarios are the outliers, the ones that fit the past worst. Here it is the opposite. The closer a model gets to reality, the worse its forecast becomes. You do not get to wave the high numbers away as alarmism because the high numbers are coming from the most accurate tools we have. And this cuts directly against the tired complaint that scientists always cry wolf and the models are always wrong. In this case, the models are being graded against 2 decades of hard observation, and the ones earning the best grades are the ones sounding the loudest alarm. When your most reliable instrument and your most frightening result are the same result, that is not noise, that is a signal. And it is worth remembering that these are 2 independent models, built by different methods, calibrated against the same real-world record, and they are not disagreeing about the direction of travel. They differ on the exact size of the loss, not on whether the loss is coming. That kind of agreement between separate tools is usually what scientists point to when they want to say the ground under a conclusion is solid. Let me translate all of this into the number that actually reaches your life, which is how high the water gets. Thwaites Glacier by itself holds enough ice to raise global sea level by about 65 centimeters, a little over 2 feet if it were to go entirely. That alone would redraw coastlines and flood zones around the world. But because Thwaites is the keystone, its collapse could help drag down the wider West Antarctic ice sheet behind it, and that ice sheet holds enough water to raise global sea levels by roughly 3 meters. That is close to 10 feet of ocean added to every shoreline on Earth. 3 meters is not an abstraction, and it is worth being specific about who is standing in the water. Coastal researchers estimate that much sea level rise is enough to displace somewhere between 500 million and 1 billion people, depending on how fast the world builds defenses to hold the ocean back. The places in the path are not remote. They are low-lying nations like Bangladesh, where tens of millions of people live within a few feet of the current high tide line, and they are some of the largest and most important cities we have ever built: New York, Miami, London, Shanghai, and Tokyo. Whether that displacement plays out as an orderly, expensive decades-long retreat behind seawalls or as something far more chaotic depends almost entirely on how much warning the world takes and how fast it builds. The ice sets the ceiling on the threat. What we do between now and then sets how much of that ceiling we actually hit, and the pace is already picking up. Global sea level climbed at about 2 millimeters a year on average since 1960, but between 2005 and 2023, that rate had nearly doubled to about 4 millimeters a year. Some will tell you this is just a natural cycle, that Antarctica has gained and lost ice before, and that is true over the long sweep of ice ages. But the rate we are watching now, and the specific mechanism driving it, Warm water intruding into below sea level basins, measured over 20 years of spreading cracks, matches a warming ocean, not a natural rhythm. The trend is not only up, it is accelerating, and it is accelerating for reasons we can name. So let me tell you clearly what this does and does not mean, because the honest version is frightening enough without exaggeration. This is not the world ending next week. The full collapse of Thwaites will unfold over decades to centuries, because a body of ice this enormous carries tremendous inertia and cannot empty into the sea overnight. Anyone telling you the coasts drown by next month is selling you a cartoon, and that kind of overreach only makes it easier to ignore the real threat. What is imminent is the breakup of the floating shelf, the cork. What follows, over the years and decades after, is the acceleration of the glacier behind it, and that part is very hard to stop once it truly begins. You will also hear that this is being deliberately hidden, or that some kind of weather technology is melting the ice on purpose. Neither survives contact with the facts. The studies are openly published in major scientific journals for anyone to read. The reason this is not on every front page is duller than any conspiracy. There's no single dramatic collapse day image. The timescale is measured in decades, and slow-moving stories lose to fast ones in the news cycle every time. As for the idea of an engineered melt, the heat doing this comes from oceans, absorbing about 90% of the excess energy, trapped across more than 70% of the planet's surface. That is a force orders of magnitude beyond anything any machine could aim at a single glacier. The culprit is diffuse ocean warming, not a beam and not a switch. What you should actually watch for is the announcement that the Thwaites eastern ice shelf has broken away from the main glacier, because scientists believe that could come at any time, and quite possibly within this year. When it happens, it will not raise the water by a single inch that day, but it will mark the moment the break came off the most dangerous glacier on Earth. 4 separate lines of evidence, published within about a year of each other, now point in the same direction, and the tools are only getting sharper. The bedrock map shows the hidden terrain that lets the warm water in. The fracture study shows the shelf's 20-year slide toward failure. The sea level record confirms that melting land ice is now the fastest growing driver of the rise. And the ice sheet models tie it together and warn that the most trustworthy of them are also the most alarming. No single one of these is the whole story. Together, they are a picture that keeps getting clearer and keeps getting worse. Antarctica feels impossibly far away. The oceans that connect it to your coastline do not. That is why a crack in a slab of ice at the bottom of the world is worth your attention today, and why the people who study it can no longer look away.